Hi everyone, I'm Erin Sweeney, so I work for Mech Mining, but I've been in the mining industry for about 16 years now. First started out as a geo, but that was over in the coalfields, and very quickly became a geotech engineer, so all of the geotechnical problems get handed over to the geologists, so kind of had to learn pretty fast a lot of the geomechanics, particularly kinematics and the like. From there, I've moved pretty much all over Australia, and I've worked up in North Queensland, Tasmania, up in over here in Western Australia, a couple of different sites. Did some time in Indonesia, in Ecuador. So predominantly what I focus on is open pits and particularly failures, so pretty significant sort of failures. During the course of my career, so I've also progressed to tech services superintendent. So I guess my perspective sort of has broadened quite a bit in geotechnical engineering, and so now I sort of have more of a business focus or a broader business focus, especially after completing an MBA. So I've sort of combined some of that information into sort of how I view geotechnical engineering. And one of the things that has sort of been pretty predominant throughout my career is understanding what's the cost of a failure. So I think as geotechs, we're pretty good at sort of, being able to control and manage failures, so knowing when they're going to happen and how long they're going to take to fail, and monitoring them appropriately. But often, like, a failure can have quite devastating consequences to a site, and I've got two examples there. The one that I personally had to deal with was at Century, which came very close to shutting that mine down. We were able to manage it more closely so that it didn't. But something that's, I think, has always sort of cropped up is, we often have this outlook that a certain amount of failure is acceptable, and it should be, but we should also be doing a bit of a financial risk assessment at first, so just to understand whether or not the site can actually cope with the failure. Is it going to shut it down? Some of the implications that sort of sit in and around that. Oh, it's not doing it for the right one. Yeah. It's moving this one, but not that one. Okay, so this one. Okay. So I really like the word black swan because it sort of describes that whole ideal of, like, you don't see it coming. So a lot of the time, a large scale failures, we won't necessarily know it's a problem. There's so many unknown unknowns in geotech. So how do you know if you're actually at increased risk of a black swan event? And how do you decide whether to be conservative or aggressive in managing the financial risks of a design? So I guess during feasibility studies, people are always sort of pushing you to a more and more aggressive design, and it can always be hard to sort of make a call about, when does sort of the tip over from being too expensive to have a failure, or too costly to sort of flatten it down. So some of the work that I've done sort of sitting in around that. So I guess this one has sort of come up for me quite a bit lately in the pandemic. So there's a lot of talk around supply chains and how we manage that, and the greatest risk for us comes at the time of greatest complacency. So if we're not sort of thinking ahead when we first start out and planning these things, then we're probably not planning for a failure. So plan for the worst but hope for the best, or that sort of mindset. We all know too little or too much failure can be costly in either way. So how do you strike that right balance? And with just data on the outside, how can you really be sure that you're getting the right balance? So have you got the right data? Have you got enough data? All those kinds of questions start to crop up. So as I said before, I think we're pretty good at the health and safety side of things. So we really get how to do this really well as geotechs. I remember the first time I got asked to risk assess these for a significant wall failure, and I was like, I don't know, what's the community impact? I didn't really feel that confident to go ahead and do that. And then sort of assessing, the process loss or property damage. So some of those things can be a little bit easier, but there are these things that I think that are a little bit tricky, and often fall to geotechs to have a perspective on, or at least to be aware that these things are risks as well, and to factor them in our design decisions. So I guess risk kind of tends to escalate itself. So, a rock fall, maybe not such a big deal. We can probably put a lot of controls in place for that. When you sort of make your way up to overall slope failure, you start to edge more and more into these other types of risks. So, reputational risk, financial risk, strategic risk. These are probably big things that, particularly in these overall slope failures, that have a huge impact. When the heat is on, you kind of got to have an idea of what these risks actually are. And I think when you sort of think back to, say, the dam collapses in Samarco and the like, that pretty much covers all of those, and sort of planning ahead for those kind of failures and understanding what they were looking like might have given you a better perspective on that outlook. And I don't want to comment too much on that, but it's certainly a good example. So the black swan, basically the idea was that everyone thought swans were white until they came to Western Australia, and then suddenly there's black swans, and so like this completely unexpected thing came up. So it's become the model for this unknown, unexpected event, and then after that point, everybody sort of rationalises it in hindsight that these things can happen, and they do happen. There's a couple of examples sort of coming up about some events that were probably unforeseen. We didn't really think that they were possible, or we maybe even thought, oh, it's fine, we'll be able to manage it if it does happen. But then the consequences were actually, in that financial stakes and the community stakes were quite high. So I guess I'm looking at this through the lens of, a mine manager or general manager. So if you're having a look at this super pit failure, which everybody sort of knows about, completely blocked off the ramp. So the guidance was 700 to 800 ounces, 800,000 ounces. What they actually were able to achieve that year was in the 550 to 600 ounces range. So equating for operating costs and the like, the price of gold as it presently is, that's probably around 300 million that they had to write out that year, just a guess, sort of doing some back of the envelope numbers. When you factor in, the delay to mining, so extending the life of mine, maybe cutting back or stepping out, all those kinds of things, other ore losses further down the track, that actually could quite easily double, if not go higher than that. So that's quite a significant loss. And then you have the flow-on effect to the community, the uncertainties, is the job there, the reputational risk to the organisation itself. So no doubt these were managed very well from a safety perspective, and I have no idea if they were foreseen or not, or if there was a sort of a decision made about this acceptability, but it just creates a really great example of something that sort of just happened, and the cost was quite significant. They've obviously come a long way since then. And then if we have a look at the Bingham Canyon landslide, so significant damage, and the estimations there was that it was almost up to $1 billion, the cost of that. So at the time, they were pretty sure that was going to shut down the pits, the flow-on effect to the community and the broader economy. Now, they've certainly bounced back from that, but it certainly, I think in hindsight, was an event that, had they known was coming, they would have probably changed a design or done something quite differently. They wouldn't have just accepted, oh, this could fail and that's okay. So, can you predict a black swan before events arises? And I think the first thing you've got to do is start thinking that this could happen to me. So when we go into feasibility studies and the like, we tend to have all this confirmation bias that sort of sits in around our designs. There's a lot of push. People really want these things to take off. And sometimes a lot of mistakes get made and we sort of don't use some of our best judgments to sort of get it across the line. But some of the errors that I've seen that have been made that sort of can contribute to some of these events. So the amount and the quality of the data that's gone into the calculations. So often we would rarely get enough data. So obviously drilling is very costly. And you're often compromising with using geodata, which may not be an exact fit. You can still use some of that data, but sort of understanding its limitations is really important. the quality of the samples themselves. So I've often seen tests that have failed lab testing, and they've been included into the data analytics as well. Some of the field assessments that we do can be quite subjective. So if you're going to estimate a GSI and I'm going to estimate a GSI, we're probably going to get some variance there, and that may or may not be margin of error that's big enough to cause a problem. That's something we need to be aware of. The robustness of the statistical analyses. So if you're sort of just using, I guess, the mean for your intact rock assessments, then that is going to expose you to a lot more risk than if you're using something in the lower quartile, and if you haven't done a full-on, probability assessment or understood statistical significance of your data, then you might be exposing yourself to more risk. So this one's probably about you're collecting samples of data from a population, and you were making an assumption that that is representative of the population, but it may not be. So the smaller the sample size, the less likely it is to be representative of the entire population. And then there's the computational analyses to determine the stability. So this is basically referring to, so if you're using slide for everything, you kind of like, it's like the hammer, everything looks like a nail. The more complicated the problem, you should be increasingly upgrading the assessment that you're using for it. So, limit equilibrium maybe for some of the more simple stuff, and then move to that finite element sort of end of numerical modelling into the equation where you're getting overall slope assessments, and the stakes are high. You want more information, you want more certainty. Just once again, I guess if your sample is too small, you're going to have not the right number. You're going to be disproportionately representing your population. If it's too big, you're going to waste a lot of money. So we don't want people just pumping money into geotechnical studies if we can sort of strike the right balance. And that answer is sort of like how long's a piece of string, and you kind of got to have an understanding of the homogeneity of your rock mass and structural issues and all those kinds of things. Just sort of garner for yourself about how much it is. But rule of thumb in statistics is sort of a sample size of around 30 is pretty standard, 30 to 40 some people say. Very rare that we would get that. So there are other means that you can use to assess a much smaller sample size to help you with some of that bias. So probably covered off a few of those points, but I guess one of the things to look out for, particularly if you're just sort of getting that spread, is your distribution really narrow or really wide. So then you're probably needing to have a closer look at what your data is, your covariance. You can often enter that covariance into a lot of modelling programs as well. And then having a think about whether or not deterministic analyses are appropriate versus probabilistic instead. So probabilistic obviously gives you a much broader range of answers and closer to a probability of failure, which is a little bit more information than a factor of safety. So rubbish in, rubbish out with factor of safety. So it's just a number really, but probability of failure, especially if you've got a really good statistical data set, it's going to give you a little bit more information. And then how do you apply some of these statistics? So John Reed's used the target levels of data confidence, and that's sort of applying your different probabilities of failures and the like to how long the wall is expected to stand up, and the level of confidence that you require for, say, overall slope to a batter scale and things like that. You can use small sample theory to help you if you haven't got enough data, to help you understand where your bias might be. Statistical significance, this sort of sits in that p-value, and that sort of requires you to sort of propose a hypothesis and understand whether or not you're testing whether or not it's representative of the population in general. Fault tree analysis, which is again sort of using some of that statistical information and your reliability of your data. So it's kind of like a sensitivity where you're sort of accumulating the reliability of data of various different elements that are contributing to the failure. Something to be really aware of, the sampling bias. So obviously if you're using a lot of geology drill holes, then they're often all drilled in the same direction, and you could be missing out on some really important information going the other way. And the Open Pit Guidelines pretty much covers most of your questions that sit in and around this. And then I guess this is just the importance of scale versus intact rock mass. So particularly if you're getting to the pointy end of the overall slope, so having a think about if you're using your intact rock mass, how have you accounted for structure in the model? So maybe you need to be using more rock mass parameters rather than intact. So thinking about where does that scale change over time, and obviously all this information is sort of sitting in that open pit guidelines, so you can go in and do a proper read. But in my experience, these are the things that are going to tell you whether or not you are more or less exposed to a black swan event. So if you haven't done a really good robust analysis and you don't have a good understanding of your weak spots, then you probably are exposed to one. But yeah, the unknown unknowns factor is always sort of sitting there in the background. So when you're actually going about estimating the cost of a failure, it can be quite ambiguous because it hasn't happened yet. You don't know what it looks like. So a lot of questions that come in: will we clean it up? Are we going to step out? Are we going to cut back behind it? How big is the failure going to be? How much ore is going to be displaced in the schedule? How much ore are we going to lose? So we have a lot of indicative data that sits in the schedule and our models that can help us answer these kinds of things. So our mining engineer friends, even though they can be a bit painful sometimes, actually do have a lot of information that can help us answer these questions. So the how big is it going to be question. So if you've done a really good model, you'll have an understanding, even if it's past the factor of safety test or the probability of failure, sort of roughly around what the most likely failure is going to be. So you'll have some data that's going to tell you it's more likely to happen here than anywhere else, usually probably somewhere around structure. And then if you're doing these more intensive analyses, then you can start to understand, why it might fail. So you can start to have a closer look at what is happening with your data in those specific areas. And that sort of gives you an indication of, the size of the failure you might expect. If you've got the size, if you've sort of got a rough volume, then you can start to work with mine planning and have a guess of, how long is it going to take, or what kind of delay is this actually going to cause to our mine. So most mining engineers will have access to a cost model, which will tell you all these different variabilities, and what you need to do is sort of break that down. They'll usually have it down to cost per tonne or a BCM, and then the next step is to get it into sort of a cost per day. So for me, that's probably the model that's worked the best. So if you can actually understand how much it costs to stop mining for a single day, so carrying all those extra overheads, and then extending the life of mine out for however long the period is that you're actually mining for, then you've sort of got a good foundational understanding of what it is. And you can throw on top of that the cost of any ore that you might lose from having a look at what's sort of sitting in the block model around there. And you can start to build up a really good rough estimation. So this is the model we use for our bow tie risk assessments, and it sort of gives you a rough indication of a number that's sort of per day. Then if you have the volume, you can start to have, or the location, you can start to build up quite a good plan about, well, it's actually going to happen in a really high risk spot, or it's probably less likely to, and so you start to get a bit of a gut feel about how these things work. One of the things that you may need to factor in is that the financial risk will change over time. So this is an example of material movement over time, and sort of this gold bit is actually where the primary ore comes out. So if it happens earlier on, then it's sort of waste stripping, and maybe it won't take as long because it's much shallower. Happens at the deepest part of the pit, and all you've got is ore, and your ore markets are relying on it, and particularly towards the end of the financial year, and there's all those guidance issues. Then that's obviously going to be a problem. So maybe running a few different models for different periods of time and trying to get a better feel for what's the highest exposure or risk period for your site. So this is a bit of an economics dust up. So some of this thinking just have applied to some of the financial assessments. So basically the idea here is marginal revenue, marginal cost. So having a look in this example, it's like, do I want to produce one more unit? In our thinking is, do we want to go one more degree? So how much is it going to cost us, or how much are we going to make? Marginal revenue, marginal cost thinking, if we go one more degree. So the idea here is that at a certain point, the cost starts to outweigh the benefits, and you kind of want to work your way into sort of what this optimal price point might be. So the more degrees you go, maybe the more profit you get, but the more likely you are to have a bigger failure that's going to take longer to clean up, and that's going to start eating into the profits that you have. So this is one that we ended up with. So we started out with sort of the base case, or the the lowest probability of failure scenario. So that's the red line in the centre, and then you have a look at what your higher impact cases might be. So how much more? So if we steepen it up a little bit more and a little bit more, then a couple of different examples, then we've got an idea of what the profitability of those might be. And so you sort of got your starting off point here. And then if a failure is to occur, how many days would it take of cleaning up for me to actually be able to break even on what it might have originally been, or how much risk am I exposed to on my lowest margin case at the bottom. So here you can sort of see that if you've got sort of around 50 days to clean up your highest risk case as opposed to your base case. So, and then you sort of got a better foundation for actually understanding how much risk am I dealing with, and can I afford to have a failure. So if it's only going to take me 40 days or 30 days to clean it up, then I'm probably better off having the failure and managing it properly. But you've got to be pretty clear on what those costs are, which is why, looking at that cost model and understanding how you can project those costs forward. So yeah, I suggest sort of setting up, model something like this to sort of help you get a better understanding. It's not foolproof, but it gives you more certainty on what the number actually is and where you're actually sitting on. Oh, is it going to fail? I don't know. How much is it going to cost to clean it up? So it's sort of, I guess it's just following that logic to understand where you might sit. And then some of the other things to think about is, so if I have a failure and I need to continue to supply ore to the market, is your operation hand to mouth, or can you stockpile? Is that part of your operational process? If you have to shut down one work area, can you start up in another? Certainly at one of the sites, and the two examples that we looked at there, that was not an option, so it was a full shutdown. But if you can sort of leverage that risk into other areas, and you can move your operation around a little bit and be a bit more agile, then you can expose yourself to just a little bit more risk, and you can sort of accept that failure a little bit more easily. And so that's pretty much it. Does anyone have any questions? Yeah.